So I guess there's a lot to say in paper 2 for radioactivity. There are 12 questions here, many pages, but I want to stick to the 15-minute limit. So let's see what we can get through. All right, number 1 shows an americium source with some alpha particles hitting some electrodes. It's a smoke detector. So this question talks about americium-241 and how the smoke detector works. Is it emits alpha particles that ionize the air. It gives the decay constant of americium, and it gives the dimensions of the chamber that it's in. So 1A says nucleus of americium-241 is 146 neutrons. This nuclide decays to neptunium through alpha emission. And then it says complete this nuclear equation for the decay. Well, you should first of all know that an alpha particle has 2 neutrons and 2 protons. So that gives a nucleon count of 4. Here we go. All right. Now, as for the americium, it's americium-241, so that gives the nucleon count, and has 146 neutrons, so based off of that, we can get the amount of protons. So there are our numbers for americium. And knowing americium and the alpha particle is just basic math to get to the neptunium. And since the alpha has 4 nucleons, that means that an americium has 241, then the difference is 237. And then for the protons, americium is 95, and the alpha has 2, so neptunium must have 93. And so that fits with the mark scheme. Okay. Then B, why is the radioactive source safe for use in a house? It's radioactive. That's a good point, because they are alpha particles, and alpha particles only travel a few centimeters in air, and the penetration is poor. You can block an alpha particle with a sheet of paper. So, yeah, of the bunch, alpha, beta, and gamma, alpha is the weakest. All right. Then deduce whether the radioactive source will need to be replaced during the life of the detector. Interesting. So based on that, we have to get the half-life. We know that half-life is the natural log of 2 over the decay constant, which is what they did here, and we get 10 to the 10 seconds. So 10 to the 10 seconds seems like a long time, but they make a good point here in the mark scheme to be like, well, how long is 10 to the 10 seconds? And I don't really see where they're getting 430 years. I'm getting 317 years. But even so, your smoke detector is not going to last, you don't need your smoke detector to last 317 years. So, yeah, the radioactive source will still be good for the life of its detector. So with the activity of the source, and it says that 1/3 of the alpha particles actually form an ion pair. And it says each alpha particle has a kinetic energy of 5.5 mega electron volts. It then says the energy to make an ion pair is 15 electron volts, much less. It said calculate the current in the chamber to the electrons when there's no smoke in the chamber. And so if each alpha particle has 5.5 million electron volts and it takes 15 electron volts to form an ion pair, you would divide the amount of energy in the alpha particle by the energy to make an ion pair. And so that's what they did in the first step here. It says each alpha could give rise to 3.67 times 10 to the 5 ion pairs, because they're dividing the 5.5 times 10 to the 6, that's the 5.5 mega electron volts, this here, by the 15 electron volts to make an ion pair. So each alpha could give rise to that amount, but only 1/3 actually does. So that's where the dividing by 3 comes from. That's the 33%. So we take the 3.67 times 10 to the 5, and then the 42,000, that's the activity rate. That's how many alpha particles are being made per second. So yeah, that 42,000 that's 42,000 particles per second. And so each particle could give rise to 3.67 times 10 to the 5 ion pairs. Only 33% of them will, so we're dividing by 3 for the 33%. but that's giving us 5.13 times 10 to the 9 ion pairs per second. Now, the problem says it's just asking about the electrons. So the ion pairs are both positive and negative. So you might be like, well, if it's 5.13 times 10 to the 9 ion pairs, it's actually twice as many. So it's 5.13 times 10 to the 9 electrons. But that's electrons per second. We're looking for amperes. And so an ampere is a coulomb per second. So that's where we bring in the coulombs per electron. The 1.6 times 10 to the negative 19 coulombs per electron. And so we go from electrons per second to coulombs per second, and that is what current is. So we get 0.82 nanoamps. That's nothing. But that's the reasoning on how you do that. So that was a 9-mark question for number 1. But number 2 over here is a 20-mark question. So let's give it a look. Talking about a nuclear power station. So yeah, number 2 is talking about uranium-235 and fission reactions. And so in that process, you start off with 1 neutron, you wind up with 3 neutrons, and that's the starting point of the chain reaction, right? So state the principal energy change in nuclear fission. The mass energy that's in the uranium goes into the kinetic energy of the fission products. I think that's just kind of like not much more to say about that. And then AAI. Energy released in reaction is about 180 megaelectron volts. Estimate in joules the energy released when a kilogram of uranium-235 undergoes fission. And we know that the mass of the uranium nucleus is 235 universal mass units because it's 235 nucleons. Okay, so this makes the energy per mass is once you look at what they're doing with the units, it makes more sense. Because what do they mean by a kilogram? How do we figure that out? But let's start with the energy of the reaction. It's 180 megaelectron volts. That's 180 times 10 to the 6 EVs. But then we want joules, so you got to multiply the joule electron volt conversion for that. And so it's 1.6 times 10 to the negative 19 joules per electron volt. And then for the mass, we're going from universal mass units to kilograms. And each universal mass unit is 1.661 times 10 to the negative 27 kilograms. That's from the data booklet. And so universal mass units cancels out. And so what are we left with but joules per kilogram, right? And so that's why they're talking about a kilogram of uranium-235. So we have 180 times 10 to the 6 times 1.6 times 10 to the negative 19 divided by 235 times 1.661 times 10 to the negative 27. And when you run all of that through, we get a lot of joules. 7.4 times 10 to the 13 joules for our answer. Okay. Then we have a chart of proton number versus neutron number. And the tellurium is not stable, but it is near the stable line. And this is similar to that chart that we've seen before. This is that chart with neutrons versus protons, where as the number of protons increases, we're going to need more neutrons than protons in order to hold the nuclei together. So that's kind of what we're looking at here. And so we want that tellurium to get back to the stable line. So it wants to know what is its decay mode. And so we can see that the tellurium is under the line of stability. So it actually could stand to be more positive. We want the tellurium to go, man, that arrow is terrible. There, we want that tellurium to go up towards the stable line, so we want the tellurium to become more positive. And if we want something to become more positive, we get rid of negatives. And so this says, state and explain the decay mode of tellurium-132. It is beta minus decay. And their explanation is that tellurium-132 has more neutrons, has a higher N to Z ratio than stable nuclides, and so beta minus will reduce that ratio or make it more positive. So there we go. Then, that's BI. A sample of pure tellurium-132 is extracted from some spent nuclear fuel from a reactor. Graph shows that the natural log of the activity of the sample varies with time. And so we have the natural log of the activity in seconds to the negative 1 versus time in millions of seconds. Okay, so for BII, it says calculate in seconds to the -1 the initial activity of the sample. And so the initial activity is when you have time 0. And I could see that the y-axis says that the natural log of the activity is 25. So I'm going to know what the activity is. So to get rid of natural log, I raise both sides, e to the both sides. I raise both sides, not to the power of e, but e to that power. So e to the natural log of a equals e to the 25. Of course, e to the natural log of anything equals that thing. And so a is e to the 25, which is 7.2 times 10 to the 10 seconds to the -1. So that's where they're getting that from. Okay, so B triple I is interesting. It says show that the decay constant is given by -m, where m is the slope of the graph of natural log of a versus t. So we start off with the activity equation a equals a naught e to the -lambda t, and we are trying to get lambda here. So we start taking natural logs. So natural log of the left side and the right side. On the right, we have natural log of a naught times the natural log of e to the -lambda t. Of course, natural log of e raised to the anything is that thing. So natural log of a equals natural log of a naught minus lambda t. And so if we restructure that expression in according to the equation for a line, we have natural log of a equals -lambda t plus the natural log of a naught. Natural log of a is the y-axis. We saw that in the graph. And the natural log of a naught is the y-intercept. That's the 25. And so what's left is -lambda t. T is the x-axis. It's on the time axis, and we're the horizontal axis. And so the slope is -lambda. The question actually asked not for the slope, but it asked for lambda. So if slope is -lambda, then lambda is negative slope. Which is what the problem says. Show that the decay constant is negative the slope of the graph, which we just did. Okay. B4. What is the half-life of tellurium-132? Okay, and so B4, BIV says, what is the half-life of tellurium-132? We know that half-life is natural log of 2 over lambda. We just figured out that lambda is the slope of this graph. And so rise over run, we get 10 over 4. Don't miss that it's 10 to the 6 on the x-axis, right? So 10 divided by 4, 10 to the 6. And so lambda, the slope, is 2.5 times 10 to the -6. Natural log of 2 divided by that gets me 277,259 seconds, which comes out to 3.2 days, which agrees with the mark scheme right over here. Okay. Then nuclear power station uses high pressure gas to empower a generator. Gas circulates between the heat exchanger and the turbine. What does the heat exchanger do? It exchanges heat, collects thermal energy, and delivers it to the gas. So that's the job. It collects the heat, but also it prevents the irradiated coolant from leaving the reactor vessel. The coolant is sealed inside the vessel. The heat gets out through a heat exchanger. There you go. Now, okay, now we have a graph of pressure versus volume. We're starting to get into thermodynamics now. So let's find the rest of this question. It's all the way over here. And yeah, then CIII talks about entropy. And then we have angular speed, radians versus time, rotational kinetic energy, and then that was that. So we're not going to get into that. This is an E3 solution video, so I'm going to cut right there. CI is the last. The rest of this is still good, but is not E3 topics. That's why this thing was 20 points. This is all about thermo. We don't need that. And this is all about rotational kinetic energy, which is interesting, but it does not have to do with E3, and with the focus here to be E3. And so that takes us to question number 3, which says what's meant by the half-life of a radioactive nuclide, and it goes from there. But I just hit 15 minutes, and I did say I wanted these to be 15-minute videos. So numbers 1 and 2, there we are. We still have many more to go. Thank you.